Good morning, everyone. I wanted to start back with this problem we were working on at the end of class. It was the last problem we worked out on Wednesday, just to kind of show something I didn't mention, which was when we were trying to figure out which one of the two reactions was limiting by a different method than we had already done. We had used this example previously, so we kind of already knew that nitrogen was the excess reactant and that hydrogen was a limiting reactant. But if we assume for this problem that we don't know that, one of the things you can do is you can always just say, well, how much of the one reactant do you need to react with all the other? And just to kind of go through this math, if we had said, well, how much hydrogen would be needed to react with all of that given nitrogen, we could go through and kind of set up the problem of just converting nitrogen to moles, using the coefficient 1 mole of N2 to 3 moles of hydrogen. 1 mole of hydrogen has a molar mass of 2.016 grams. And I just wanted to show here that this would take more hydrogen than what we have available. So we would need 3.24 grams of hydrogen to fully react with 15 grams of nitrogen, but we only have 2.5 grams of hydrogen present. So with only 2.5 grams of hydrogen available means that we can't use that much hydrogen. That means that nitrogen's not going to be the limiting reactant. So this is one way, if you went through a problem like this, if we were asked to identify how much excess reactant remains, we didn't already know the limiting reactant, I would just either try to make a guesstimated guess on which one's the limiting reactant, but if I made a mistake and chose the wrong reactant, I just go through the problem a second time. I just go through the problem like we worked through on Wednesday with the hydrogen. We know that's the limiting reactant, or if we didn't know, we could show it's a limiting reactant by converting it to moles, using the mole ratio from the reaction, converting to grams of nitrogen, and seeing that we only need 11.58 grams of nitrogen. We have 15 grams available. So we're going to react 2.5 grams of hydrogen down to 0. We're going to take 11.58 of the 15 grams of nitrogen and leave behind the remainder. So we're going to leave behind 3.4 grams of the excess reactant, in that case being nitrogen. So last time, I don't think I had concluded or shown how you can definitively show with the calculation, with just this one calculation that we had done last time, we could show that through this one calculation, through seeing the excess nitrogen, that indeed nitrogen's the excess reactant, and had we chose the wrong reactant, we would have seen too much of the other reactant was needed compared to what was available. So whenever we're working stoichiometry problems, it's just the only way I think we can get through them successfully every time is just by having a lot of thought in the setup of the problem, a lot of thought in when we're using gram to mole conversions to convert to moles, when we're using the coefficients in the reaction to balance out moles of one reactant to the other, and etc. So let's look at this problem here. Let's do this one together. So we have 12 grams of hydrogen. So it says when 12.0 grams of hydrogen reacts with an unknown amount of oxygen, so we don't know how much oxygen is reacting, that we produce 76 grams of water. And so then we're asked how much hydrogen remains and how much O2 had to have reacted if the reaction had proceeded to 100% yield. So this isn't a problem where we're seeing a limit in how much product's made. So we have 100% yield taking place, the reaction's going to complete yield. From the amount of water that's produced, we could work out how much hydrogen had to have reacted to produce that quantity. So one of the things we could work out with dimensional analysis would be the number of grams of hydrogen that had to have reacted to produce 76 grams of water. So we had 12 grams, but it doesn't mean all 12 grams converted into the water. So let's take the mass of water that had formed, and then let's think about grams per mole for water. So it's 18.02 grams per mole of water. We're given the reaction here. For every 2 moles of water, 2 moles of H2 had to have reacted to produce it. So just using our coefficients here. And then 1 mole of hydrogens, 2.016 grams. And so I can work that out with just a simple dimensional analysis step on how much hydrogen had reacted. So let's run through this real quick. So I get 8.50. Now, the one place to be careful of is that that's not the hydrogen that remains, that's the hydrogen that reacted to produce the water. We had 12 grams of hydrogen, so the mass of hydrogen that's left over is 3.5 grams. So we have 3.5 grams of H2 that remain after this reaction is completed. So I have 3.5 grams of hydrogen that are left over once this reaction had reacted to 100% yield. Now, how much O2 had to have been produced? Or excuse me, how much O2 had to have reacted to produce this much water? Well, we just go through this problem again for number of grams of oxygen to produce 76 grams of water. And I can work through that, and hopefully you guys see that step too. But let's think for a moment, let's side tail into a BCA chart real quick and kind of see how a BCA chart could help us solve this problem too. We don't necessarily need to use a BCA chart. We could just use dimensional analysis. But if you were sitting there thinking, well, could we have thrown this somehow into a BCA chart? The only thing I might do here is just remember that I'm going to want to put moles into the chart. So I'm going to want to take the 12 grams of hydrogen initially present, divide by 2.016 grams per mole, and come up with 5.95 moles here. So I want to put moles into the chart, and not grams, because my reacting unit, when I want to put minus 2x minus x plus 2x, where x is just a ratio, for every oxygen lost, we're losing twice as much hydrogen, but we're gaining twice as much water. So I'm just using the coefficients in my reaction to get the number, and then reactants are lost, products are gained. And then after the reaction's completed, I get 76 grams of water. So when I convert that to moles, so 76 divided by 18.02 is 4.22 moles. Now, the reason why I often skip BCA charts is because you got to do too much math to throw the numbers into it. So you're like going to the calculator and coming up with numbers where we could have just went into one-dimensional analysis step. So to me, dimensional analysis is easier, but a BCA chart may help us understand what's going on here. It shouldn't necessarily complicate things. It's just an alternate approach. And so the approach here, if you can see this step here, is we can solve for x. And so if you set the chart up this way here, we could determine that x would be equal to 2.11 moles. And so when we don't know initially how much O2 was present, but we do know that however much of it that was present, that it must have been the limiting reactant, because we already calculated we already calculated hydrogen remains, so oxygen has to go to 0. So however much of it that was present had to have reacted. So we needed to have 2.11 moles of oxygen present, so we could lose 2.11 moles, go down to 0. So the number of moles of oxygen that had to have reacted would be 2.11 moles of O2. And it's 32.00 grams per mole. So that's 67.5 grams of oxygen. And then if you want to double check hydrogen and say, okay, can we just make sense of the hydrogen number we already calculated? So it should be 5.95 minus 2 times 2.11, because x is just 2.11. So I'm just plugging this in for x. And then I would get, in terms of the number of moles of H2, put a multiply sign, 5.95 minus 2 times 2.21, not 2.1. 2.11 moles is x. So this gives me 1.73 moles of H2. Which gives me 3.49 grams of H2. So 3.5 grams of H2 remain. So to me, BCA chart's a little messier. You're converting between grams and moles more liberally. We can do that. We can use the chart, hopefully help it have our understanding of the problem. The only nice part I like about the BCA chart is seeing the relative change and how you can solve for X, and it just gives us a problem-solving tool. Now, if we go back to dimensional analysis real quick, I think by far it's the faster way, because for oxygen, we're just using that same step here, 18.02 grams per mole of water, and the coefficient changes for every 2 moles of water that are produced. In the reaction, we had to react 1 mole of O2, 1 mole of O2, 32 grams. So within one line in our calculator, we can solve the problem just to double check. And I get 67.5 grams. So there's always going to be more than one way to solve a problem. Hopefully, if we have 2 or 3 ways we can think through a problem, like I said on the test, you just have to have one successful way. So hopefully having different ways we can think through the problem all help us get toward the right answer for problems like this on exams. So let me throw this one to you guys here. This kind of goes back almost to the start. We started with a particle question. Let's end with a particle question from chapter 3. So today's survey, the key word or the password is electrolyte. So you can answer this as question 1. Feel free to work together. Take about 2 or 3 minutes for this. I don't think we're going to come back into a quiz. I forgot to put the open-ended survey. I screwed up last time on if you had feedback on the exam. So if you wanted to leave a little exam feedback, you can do that now before you submit this quiz. So we'll probably give like 3 or 4 minutes for this one. All right, let's take a look at this one here. So we have, one thing I thought might be confusing in this problem was we didn't tell you which one of the molecules was F2, which was Cl2. It doesn't matter, right, because we have the same number of each of them. So I'm going to assume these are the F2s, just if I start to kind of think of reacting. I'm going to need to also write this reaction that I have F2 and Cl2 combining to form ClF3. So we need a 2 here to balance, and then a 3 here to balance. So I have to kind of think about balancing this reaction. So if I take 3 of the F2s and 1 of the Cl2s, And if I do that twice, I'm going to take all 6 of the F2s. So I'm going to lose all the F2s, but only 2 of the Cl2s. So I'm going to leave behind 4 chlorine molecules. So I'm going to have 4 Cl2s left over. Then I'm going to produce the 4 ClF3s. And so that should be all 12 of my fluorine atoms. And then 2 of the molecules of chlorine reacted, so 4 chlorine atoms. And so we could also have gone one at a time and kind of taken and formed 2 ClF3s from half of the fluorines that we're going to react, and then get another 2 ClF3s when the second one reacts. So this diagram here, we can go through this also through dimensional analysis if we wanted to. We could say if we're losing all 3 down to 0, for every 3 of, if we have 6 F2 react, well, for every 3 of them, we get 2 ClF3s. So that's how we get 4 ClF3s by using math, too. So if you're stuck on the picture, let's just go back to math. Okay, so it ends up being answer E. I don't know why the computer is saying there's a right answer here. So if you submitted it and said A was the right answer, just ignore that. I don't know, something's screwing up on this quiz. Okay, so that kind of takes us through chapter 3. There's more quiz problems if you need to see more review. Definitely work on that stoichiometry. Just the section 6 and 7. Midterm 2 is not cumulative, so we're just focusing on the new material when we get to midterm 2 in a couple weeks. So our midterm is going to be through chapter 4 and also part of chapter 5. So let's start our discussion here today of chapter 4. So chapter 4 is on the topic of aqueous reactions. So that's just a fancy word for reactions in water. And properties of solutions as well. So we're going to talk all about water, things dissolved in water. And so we're going to talk about some properties of aqueous solutions. We're going to talk about precipitation reactions, also sometimes called metathesis reactions. These are where you start with solutions that, where you have 2 solutions, mix them together, form a solid. And so we have something precipitate during the reaction. We'll talk about acids and bases and their neutralization reactions in the middle of the chapter. These are just meant to show this is kind of the second half of the chapter. We'll get into redox reactions. That's where we have oxidation reduction taking place. We'll talk about concentrations of solutions, how we could look at things like molarity, where that's the moles of a solute per liter of the solution. So that's how we can express how much of something is dissolved into the solution. And then we can do problems related to stoichiometry for these solution problems. So we can solve problems that look like chapter 3 problems, but instead of mass and molar mass, we give you molarity and volume, from which you can calculate moles. And we can solve problems that look like chapter 3 problems here in chapter 4. So we'll be reviewing some aspects of stoichiometry towards the end of the chapter. And so let's start with what it looks like when compounds or different types of substances dissolve in water. So the first kind of example is NaCl dissolving in water. And one of the things you can see in this diagram is that what water is doing is it's kind of plucking off each individual ion kind of one at a time from the salt crystal. We've mentioned a lot of times that ionic compounds are a little different than molecular compounds because they have these built-in charges. They have the ions of plus, minus, plus, minus, plus, minus. And then those ions end up having a strong attraction for water, which is why they end up dissolving in water kind of in the first place. You can imagine that the ions have an attraction for each other, then they also have an attraction for water, and it becomes kind of a question of which of those attractions is stronger. There's also a concept called entropy that we discuss later in chapter 19, where that's a major disorder. We have more disorder if the thing dissolves into water, so that's a driving force as well. But one of the things that we're going to see is not every ionic compound dissolves in water. We're going to see that some compounds do, some don't. We're going to see that there's some general guidelines that we can use called the solubility guidelines to help us predict which compounds are soluble versus insoluble in water that are in this ionic compound kind of classification. But then we also have molecular compounds can mix with water. And in general, we don't talk too much about things that are soluble versus insoluble for molecular compounds, but we'll just talk about the things that do mix in water and try to come to an understanding of what it would mean for them, those sort of things to ionize. So we could have methanol shown here, where it's not ionizing at all. And one of the reasons is you can say it's not an electrolyte, or it's a non-electrolyte in water. And so not all molecular compounds that dissolve in water ionize. So something like methanol can have a mutual attraction with water. We'll talk about that attractive force in chapter 11. It's the hydrogen bonding force of attraction if you've seen it. But molecular compounds don't have to go through this process of ionizing like the ionic compounds do, because the ionic compounds are already ions. In order for them to dissolve in water, they're just separating where they then are released as their individual ions. Since molecular compounds aren't ionic compounds, they don't already have these built-in ions and aren't going to like fall apart and dissociate when they hit water. Now, some things do. We'll talk about acids and bases, but before we get into that, let's just take a look at a quick little demo here. So I just kind of made a quick list of a few compounds. What we're going to do here is try to really see what it means for something to be an electrolyte. So we're going to look at water first and try to see if water in and of itself is an electrolyte. In fact, we might have to see an electrolyte just to make sure these light bulbs light up, because when you see the first thing where this is just water, so the first reaction, you may not, like nothing lights up. And let's see the second reaction just to make sure that if we put an electrolyte into water, then we can see the difference, and to make sure the light bulbs actually work here. So this is just pretzel salt. And then we also get a sugar packet kind of going into another glass. So this is just ordinary table sugar. So this is sucrose. So let's see if this is enough to light up our light bulb. So there, just making sure our light bulb works. Because with the water, you could have just said, well, maybe the light bulb wasn't working at all. But what we have here is an electrolyte. So what we can say so far is that water didn't cause the light bulb to light up. So water in and of itself is a non-electrolyte. And let's talk about the light bulb real quick. The light bulb, there's two electrodes in the water. If I could put a piece of copper between them, then the copper would serve as an electrode to light up the light bulb. And so what the ions are doing is they're acting as an electrode. The ions are just taking the positive charge, hits a negative ion, then hits a positive ion, and they just alternate the charge through the ions, and they serve as the wire that lights the light bulb up. And so the NaCl is acting as an electrolyte. We actually call this a strong electrolyte. We'll see a weak electrolyte in a minute to kind of contrast how bright that light bulb was for something else that lights it up a little bit, where water doesn't light it up at all. So the implication, or actually write that in here, implication. So we have very few to no ions in solution for water, for just the pure water. So SOLN solution. So for water, not really ionizing. Now, you might say that water has a pH of 7, and that would mean that water has about 10 to the minus 7 molar H plus and 10 to the minus 7 molar hydroxide ion. That's so few that that's not enough ions to light the light bulb up. So really few to no ions for water, but then we see Na plus and Cl minus ions. And so those are the ions that are acting as the electrolyte for the sodium chloride solution. And so let me try the sugar solution real quick. Let me go back to the water too, just to make sure we've cleaned off all of the residual NaCl from the previous solution. So this is our table sugar, which it hasn't completely dissolved. Maybe we can look back here later once it dissolves a little more too, just to make sure. But the table sugar is not an electrolyte, so I'm not expecting it to light the light bulb up. You might be sitting there thinking, well, it hasn't really dissolved completely, getting there, and just to make sure, not lighting that light bulb up, okay? And so not seeing the light bulb light up means that our sucrose or our table sugar is not an electrolyte. So that's also what we would say is a non-electrolyte, because it's not lighting the light bulb up. Let's look at an acid. Let's look at hydrochloric acid. So this is hydrochloric acid here. So that's really bright. That's bright just like the NaCl was. And so I have a strong electrolyte for my HCl. Now let's look, let me clean this off. So what about any other acid? So do all acids do the same thing? Let me just choose another acid, acetic acid, and give it a try. And you see how it's, I think you guys can see, it's barely lighting the light bulb up. And so barely lighting that light bulb up is what we then call a weak electrolyte. So HCl lit it up just like NaCl. So we have a strong electrolyte here for HCl. But then we have a weak electrolyte for the case of acetic acid. Now, what's the difference? Well, the implication is that the HCl is completely ionized into its ions. So we can imagine what must have happened for HCl is just all of its molecules ionized to H plus and Cl minus. So we remained with no HCl molecules intact as an actual molecule. So we ended up getting complete ionization for HCl. But then for the acetic acid, we only got some ionization. So we must just be getting partial ionization. So partial ionization. So we're getting some H plus and acetate ion. Then we're also mostly still intact with the acetic acid molecule. So mostly undissociated acetic acid would be the implication for acetic acid. So some of it's dissociating. We'll write some reactions for this later. We get some dissociation, but mostly we just have the intact acid that hadn't dissociated, but it's completely mixed in water. So it's still dissolved in water. It's not sitting at the bottom of the flask in the form of a solid or anything like that. One of the ways we might write this would be we have acetic acid in the solution. We might write that AQ to show that it's an aqueous solution dissolved in water. And then we get this equilibrium to acetate ion and H plus ion. And that we're just doing this to less than 100% yield, so to maybe only about 5 or 10% yield. So we're mostly on the reactant side still. So we have mostly reactant, but just a few of the products. And this becomes a topic that you'll spend a lot of time on more in 1220 of what we call dynamic equilibrium. The idea that in the flask, we always have at some moment some molecules dissociating, and then some other molecules recollide and go back to the reactant side. So we always kind of have the forward reaction taking place. We always have the reverse reaction taking place. You'll see that you could say those reactions, when they're at equilibrium, take place at the same rate, so that you always have some forward reaction taking place and some reverse reaction taking place. Meaning molecules are always colliding and going back to the reactant side, and the reactants are always dissociating and going toward the product side. But then if you look at HCl in contrast, that HCl, AQ, is just 100% H plus and Cl minus. And that effectively you never recombine to reform HCl, so that you're always in the H plus and the Cl minus case. And then we give terms to compounds that are making H plus. We call those acids. So anything that makes H plus is an acid. So we call acetic acid a weak acid. And then HCl, this molecule, we call it a strong acid. So it's a strong electrolyte, but strong acid, Sa. So we have strong acids, we have weak acids. Weak acids partially ionize, strong acids or strong electrolytes completely ionize. So let's just cap off looking at what we call a couple bases. So the H plus ion is what we call an acid. What do we call a base? Well, a hydroxide ion is the opposite of an acid. If you combine H plus with hydroxide, you make water. And so hydroxide ion containing compounds, or compounds that release hydroxide ion into water, like sodium hydroxide, we call those bases. I'm going to clean off the electrode. So this is sodium hydroxide. That's a strong electrolyte. And then one other molecule to look at is ammonia. Now, ammonia is what we're going to see, it's also a base, and it just barely lights that light bulb up. So this is a weak base. Okay, so let's see what we can conclude for the bases here. So we have sodium hydroxide. That completely ionized. That's our strong electrolyte. It's also a strong base because it's releasing hydroxide ions into solution. So we get the ions sodium plus and hydroxide ion to 100% yield. And then ammonia is a weak electrolyte because it partially lit up the light bulb, and we call it a weak base. And we get some ionization, we'll see, to NH4 plus, and then hydroxide ion. So we're only getting some of those ions. Let me actually write that in as like less than 100% yield to imply that we're not getting the complete formation of those products. So let's look at those reactions real quick. So sodium hydroxide is just like any other ionic compound that when it dissolves in water, the solution process is ionization. It ionizes the sodium and that hydroxide ion. We kind of like go back to nomenclature. When we see an ionic compound, we're like, how do we name it? That's sodium hydroxide. And then so it releases sodium ions, and then it releases hydroxide ion into water. And then this thing being what we call a base allows us to call sodium hydroxide a strong base. It's also a strong electrolyte because we're ionizing it completely. And then ammonia, what it's doing in water, NH3 reacts with water, where the nitrogen is taking an electron pair to form NH4, or it's taking the H plus ion off of water to form NH4 plus ammonium, and then leaves behind hydroxide ion. But it's just doing this in one of those equilibrium reactions where we get less than 100% yield. Think of the ionization reactions of ICs like sodium hydroxide being strong electrolyte just means 100% yield on that ionization reaction step. But NH3 does this partially. We call it a weak base. It's a weak electrolyte, so it's a weak base. All right, so this is meant to be like a quick introductory activity that looks at comparing a large set of molecules. We're going to then come back and talk about each of these classifications of compounds. So we're going to talk a lot about ionic compounds for a bit, then we're going to circle back and talk about acids, go back through what it means to be an acid, and then go back through what it means to be a base. So we're not trying to say, okay, we're moving on to section 4 now. We've covered everything. We're just trying to give a quick little precursor and a quick glance into some of the different properties that compounds have in water. So one of the things you might be seeing is that that real quick, all of the ICs that are water soluble are strong electrolytes. So ionic compounds are kind of easy to classify. It's like, is it water soluble? Yes or no. If it is, it ionizes. What do you think it does if it doesn't dissolve in water? It doesn't do anything. It's the bottom of the test tube. It doesn't change the properties of water at all if it doesn't dissolve. Okay, so one of the summaries we can see here is that a strong electrolyte is a solute. It's a substance that dissolves in water that fully dissociates into the water. So the solute dissolves into the solvent to create a solution. And then if we get ionization, it's lighting up the light bulb. And so lighting up that light bulb is what makes something be called an electrolyte. And it's the ions that serve as the electrolyte. So you have to have ions in the solution for the solution to be electrolytic. Just remember, water by itself, relatively few ions, didn't cause the light bulb to light up. So we need ions to be present to be an electrolyte. If you get a few ions, we call that a weak electrolyte. So partial ionization is what we call a weak electrolyte in water. So weak electrolyte is a solute that ionizes somewhat. So an example of a weak electrolyte in water could be NH3, or it could be something like acetic acid. So the examples here would be weak bases or weak acids. So molecular compounds you might be seeing a little more complex than ionic compounds. Ionic, it's soluble, strong electrolyte. If it's molecular, it could be a weak acid, could be a weak base, where you get partial ionization, or it could have been like HCl, where you got complete ionization for strong acids. A non-electrolyte is a solute that mostly stays intact, doesn't ionize at all in the solution. So examples of this from the previous example would have been, well, we didn't look at it here, but from the picture was methanol, sugars, and most of our other molecular compounds. So most molecular compounds that are not acids or bases are in this category of being compounds that don't ionize at all in water. So then insoluble compounds, something that just doesn't dissolve in water at all, it's not a solute. So in order for something to have a property of a solute, it has to dissolve. And so when we say something like, for example, lead chloride is insoluble in water, meaning it doesn't dissolve into the water at all. So if we said, what type of solute is lead chloride in water, you would say, it's not any kind of solute. It's not applicable to give it a term you give solutes. So sometimes I've seen people say lead chloride is a non-electrolyte in water. It's not a non-electrolyte. It had to have dissolved and not ionized to be called a non-electrolyte. Lead chloride just doesn't dissolve at all. So it doesn't take any term that we give a solute because it's not a solute, because it's insoluble. Okay, so how do we know for ionic compounds if it's water soluble or not? Well, the main reason, or the main way we would know this, is through using solubility guidelines, like a chart like these. These charts here are given on exam, like this chart almost in this exact format, it's given on exams. And then all water soluble compounds on this chart, all the compounds we can determine are water soluble using this chart would fully ionize and completely ionize in solution. And all the compounds that are insoluble, of course, wouldn't ionize because they didn't dissolve into the solution. Okay, so what are the general compounds that are water soluble? So nitrates and acetates, no matter what metal atom you pair up with them, are soluble without any exception. So you take any cation, there's so many examples. You could have like copper 2. So copper 2 is copper 2 plus. So a nitrate, NO3 minus, could be 2 of them. So CuNO3 of course, would be soluble in water. We could write that AQ, meaning it would ionize into copper 2 plus ions and 2 nitrate ions. Meaning that those ions would dissociate from each other. But notice that the molecular ion nitrate doesn't dissociate further. Remember, like I said earlier, if you can name the compound copper 2 nitrate, it's going to dissolve to copper 2 ion, and it's going to dissolve to nitrate ion. And then those ions are what form in solution. And so the nitrate ion is a stable ion. All of our polyatomic ions that we named are stable if they hit water. So we also have chloride, bromide, iodide that are soluble. So notice, let me point something out here. The soluble ionic compounds contain these ions. So nitrates, acetates, soluble without any insoluble exceptions. Chlorides, bromides, iodides, almost all are soluble, but we have 3 exceptions, the same 3 exceptions for each: silver 1, mercury 1, lead 2+. Okay, remember the mercury 1 ions, that goofy Hg2 2+? We saw this in nomenclature. We didn't do too much with it, but Hg2 I2 is mercury 1 iodide. How do I know this? Well, iodide's only an I- ion. That's what iodide is. So there's 2 of them. That's a 2-. So my 2 collections of mercuries here has to have a 2+ charge. So this is the mercury 2+ ion. And we give that the common name of mercury 1. You would think mercury 1 is this, right? From naming, you would think that's mercury 1. But mercury 1 are those 2 atoms bonded together, kind of like peroxide. I have 2 oxygens bonded together, each with a minus charge. Here it's 2 mercuries, each with a positive charge with some kind of bond linking them together. And then we have I- on either side. And that this is an insoluble exception. So this compound here would be insoluble in water, wouldn't be aqueous, wouldn't dissolve into water, wouldn't dissociate into water at all. And the same thing with silver, be AgI, and then PbI2. And now, just to complicate things, mercury has another common ion. Silver doesn't, lead really doesn't under most circumstances. Lead might form the lead-4 ion, but that's in highly acidic environments. But lead primarily only forms the +2 common ion in stable compounds. But mercury forms a 2+ ion, just the ordinary mercury 2 that's not a listed exception. This would be HgCl2 if it were to pair up with chlorine. This compound here is water soluble. But then if you put the 2 in front, Hg2Cl2, this is insoluble. See how silly that is? But one of the things I think is useful to know is that mercury has 2 common ions. Mercury 1, the goofy Hg2 2+, and the ordinary mercury 2, Hg2+. And the ordinary Hg2+ is completely ordinary. It fits the category of being soluble. It's maybe worth noting also that solubility isn't really a yes or no question. Solubility is always a range. Every compound that we say is soluble does have some soluble limit, and some of those limits sometimes are actually pretty low. So some compounds, even though we call them soluble, may not be very soluble. They may only be soluble to a couple grams per liter. But then if you're below about, I think it's 0.01 moles per liter soluble, if you have a solubility lower than that limit, we say it's insoluble. So even the things we say are insoluble have some reasonable solubility. So it's something to keep in the back of your mind, is that solubility is really a range. You come back to solubility topics in a way worse way than we talk about it here in chapter 17. You'll hate it when you see it, I'm sorry. But it's very detailed because you can look at what you call solubility product constants, where you can actually get a measure of the actual solubility of different compounds and solve all kinds of math problems based on it that you will see when you get there. So solubility really is a range. Here in chapter 4, we're just trying to say soluble versus insoluble using some general guidelines. So for the chlorides, bromides, iodides, 3 compounds are insoluble. Any other compounds of those ions are water soluble. For sulfate, it's strontium, barium, mercury 1, lead are insoluble. And then all other compounds would be water soluble. Now the important thing to remember is you get the chart, so you don't have to memorize the chart. You just have to remember some nuances with like mercury, and you have to just know to consult the chart if you're not sure. And just that the top half of the chart are showing us are generally soluble compounds, and then the bottom half of the chart are generally showing us are insoluble compounds. Insoluble compounds tend to contain things like carbonate and phosphate. Let me take one little quick detour and mention something not on the chart. That is this fact here, that all ionic compounds of the alkali cations and ammonium are water soluble. I wish they would put that on the chart. I wish like the soluble chart had the alkalis and ammonia listed, because there's no practical common exception to this rule. Because what this allows us to know is when you look at carbonate and phosphate, that you can at least know that the alkali and ammonium cations have to be water soluble, and you see those are listed exceptions here. So ammonium and the alkali cations soluble with carbonate and phosphate, and then sulfide and hydroxide, never understood why they separate them in the book. Yet the hydroxide, sulfide, top and bottom of the chart have the same exceptions. I don't know who came up with this chart. It's been this way for like multiple editions, so somebody thinks that they should be separated. But if you notice sulfide, compounds of ammonium, alkali cations, but also calcium, strontium, barium, same exceptions listed for hydroxide. So hydroxide and sulfide have the same exceptions of course, ammonia and the alkali, but also the heavier alkaline, so calcium, strontium, barium. But anything else with these ions are water insoluble. Okay, so the exceptions here are soluble, because these compounds are generally insoluble, and the top half of our chart are soluble compounds, or the exceptions are insoluble. Just have to keep the two charts, the top and the bottom half of the charts, kind of clear in our minds on how we use the chart. Okay, this question is really easy because hopefully it's easy, but let's come back to a simple question. If I'm honest, this question is like always missed on exams. Like questions like this have appeared in exams for a while, where we just this thing's called potassium nitrate. And potassium nitrate, when it hits water, would become potassium ions and nitrate ions. And the nitrate ion doesn't further dissociate, so we would just have potassium and nitrate ions in solution of KNO3. But this answer here, like a lot of people go for B. Not sure why, because it doesn't even have the right balance of charge. If you think of nitrate falling apart, if it went to oxide, nitrogen would have to go to like a cation. But it's important to recognize that KNO3 is not a collection of nitride and oxide, it's a collection of potassium and nitrate ion, where nitrate ion is nitrogen, 3 oxygens overall minus charge. So our polyatomic ions and compounds, those are going to remain intact. So the next two questions are kind of just going to make us write a bunch of formulas and think about a bunch of different formulas. So the first question here is saying, write all the water-insoluble compounds of chloride, bromide, iodide, and sulfate. Because there's, from the previous chart, it may make it seem like there's way more exceptions, but there's just the exception with chloride of AgCl, PbCl2, then Hg2Cl2. Like, that's it. Those are the only insoluble exceptions for chloride. And then the only one you might get confused by is HgCl2. That's soluble, so that's not an exception. So just making sure that we see for silver, mercury, lead, there's one other common ion of those three that would not fit the category being insoluble. So for bromide, same thing. So we got silver bromide, lead bromide, mercury 1 bromide. And of course, we're not going to include HgBr2 as one of these exceptions because it's not a listed ion on the chart. We can write the silver iodide, PbI2, Hg2I2. And of course, we're not including HgI2. Now, I don't know if the formula Hg2Cl2 bothers anybody as not being an empirical formula, but it shouldn't necessarily bother you for not being an empirical formula, much like if we wrote sodium peroxide, we'd have Na2O2. A compound should be the empirical formula of the ions, so the simplest ratio of the ions. And Hg2 2+ can't be broken down further because it's a molecular cation. So the ratio of the ion, this is the ion, so I can't break it down. I can't divide that by 2. That's why we don't write these as HgI or HgBr, but rather Hg2I2. With sulfate, we'd have the mercury 1 sulfate, so Hg2SO4. Sulfate's a 2-, so lead sulfate, PbSO4, strontium sulfate, and then barium sulfate. So those are the only insoluble compounds of the ions that are given on those charts. Now you may be wondering, what about other ions that we don't see on the chart on the top or the bottom? Well, they just have more complex solubility rules that would fit into a chart like this. So for the other anions that you don't see on the top or the bottom half of the chart, don't worry about their solubility trends, other than knowing that they could pair with alkali cations and NH4+ and be soluble, because we see all compounds containing alkalis and ammonium are water soluble. So we're asked to give a few water soluble exceptions because there's so many exceptions, or so many compounds are soluble that contain these ions. So what are some compounds that are soluble? Like literally anything that's not the ones we wrote above. So you could have like calcium chloride, you could have copper 2 bromide, you could have iron 3+ with sulfate 2-. So Fe2SO4 would be water soluble. With iodide, again, anything. Barium, iodide, BaI2 would be water soluble. List some examples of water-soluble ionic compounds of hydroxide, sulfide, carbonates, phosphates. So the ones that you could write, like potassium with anything's water-soluble. So you can have potassium hydroxide, you can have K2S, K2CO3, K3PO4. So alkalis with all these would be water-soluble. But if you paired like calcium, it would only be calcium hydroxide that's water soluble and calcium sulfide, but not with carbonate and phosphate because it's not a listed exception. There's some examples of water insoluble compounds. So what are examples of an insoluble compound with those ions? Literally anything that's not a soluble exception. So like copper hydroxide, water soluble. Magnesium's not on the list anywhere, so magnesium sulfide is insoluble. A carbonate, calcium carbonate's insoluble. Aluminum phosphate would be water insoluble because it's not a listed exception. So then any ionic compound paired up with ammonium or alkali cations are soluble. That last kind of rule we saw on the chart. Anything you pair up with an alkali or ammonium, so NH4SO3, so 2 of these, that's water soluble. Pair potassium with anything, with CO3, where you did that one, but K2CO3, water soluble. So pair alkalis or ammonium with anything, and they're water soluble. Okay, that's where we'll stop today. We'll pick up with the precipitation reaction and writing out some reactions for these types of things next time. Have a great weekend.